We have part 284C3m1b7c8e13c2, and it's line 22f1fa19c3m1b7c8e13c2, quantum Hall Boltzmann, Quasiparticles UFO 5G Wow Seti. There's the alien radio signal, and the keyword research, core structure designs, the UFO spaceship math equations will be covered in this video. So December the 7th, December the 7th, 2012 is when I was working on it. Today is January the 30th, 2013. The keywords to research from the data from the previous video are line 22f1fa19c3m1b7c8e13a, quantum transport, nanodevices, UFO 5G Wow Seti. It was one of the previous videos, which is back about 20 videos. And then the actual previous video now, as of January the 2nd, 2013, is line 22f1fa19c3m1b7c8e13c1, Wigner, molecule, quantum crystals, UFO 5G Wow Seti. So you can see there's a lot of videos between 13a and 13c. So the quote from Wiki is fractional quantum Hall effect. The fractional quantum Hall effect is a physical phenomenon in which the Hall conductance of 2D electrons show precisely quantized plateaus at fractional values of E squared divided by H. Is a property of a collective state in which electrons bind magnetic flux lines to make new quasiparticles. And excitations have a fractional elementary charge and possibly also fractional statistics. The integer quantum Hall effect, list of publications. At high magnetic field B, the electronic density of states becomes a set of discrete Landau levels due to the confinement produced by the field. The following diagram shows the Fermi circle in two-dimensional K-space with a series of Landau levels inside it. Okay. This is Fermi circle in 2D. Quote from blog: when these levels are well resolved, if a voltage is applied between the ends of a sample, the voltage drops between voltage probes. Excuse me. Hey, sorry, I had an important phone call, so I have to restart filming this again. It's part 284C3m1b7c8e13c2, line 22f1fa19c3m1b7c8e13c2, quantum Hall Boltzmann, Quasiparticles, UFO 5G Wow Seti. And I think we're talking about the Fermi circle in 2D. That's where we were. Okay, so quote from the blog: when these levels are well resolved, if a voltage is applied between the ends of a sample, the voltage drop between voltage probes along the edge of a sample can go to 0 in particular ranges of B, and the Hall resistance becomes extremely accurate, quantized, the quantum Hall effect. Special values of field are those at which the ratio of the number of electrons per unit area to the numbers of units of flux, He, is an integer. This ratio is called the filling factor and is denoted by the Greek letter nu. So this is an integer and fractional quantum Hall effects graph. The QHE can be described in terms of a set of states, one per Landau level, traveling along the edges. The nature of the edges of these edge states is of great interest, and much work has been done to try to examine their structure and the way in which they modify the potential of the edge. And this is from www.sp.phy.cam.ac.uk. Quote from blog. Here's spin, pseudo-spin, and entanglement. Okay. Entanglement Skyrmions in multi-component quantum Hall systems. Quotes and diagrams are from a blog. Electrons moving in two dimensions subject to a strong perpendicular magnetic field exhibit a wide variety of unusual many-body phenomena. The most celebrated of these are the quantum Hall effects, after which the field of their study is named. These effects appear when the number of flux quanta is commensurate with the number of electrons in the system. Near commensurability, the elementary excitations can be non-trivial, charged-up spin textures known as Skyrmions. We have studied the properties of Skyrmions in systems with several internal degrees of freedom, such as graphene or bilayer systems. We have found that even in the presence of anisotropies, there are families of degenerate skyrmions which differ in the degree to which the different internal degrees of freedom are entangled. We discovered that there exists a unique, most entangled topological excitation, which we call the entanglement skyrmion. Fundamental aspects and applications of spin-coherent Boltzmann equations in graphene and spintronics. Here's a graph there. Dirac regime, and it shows electrons and holes. Okay. A sketch showing a simplified picture of the conductivity in monolayer graphene with screened charged impurities. Far away from the direct point, the conductivity follows Drude result with a linear behavior as a function of carrier density. However, because of the electron hole coherent quantum effects, there can be a small shift to the Drude result. Graphene is in the simplicity a fascinating system both for applications and for addressing fundamental issues. In our case, graphene prompted a re-examination of several common approaches for deriving Boltzmann-type semi-classical kinetic equations from non-equilibrium quantum many-body theory. Such semi-classical equations provides also in quantum systems a powerful and intuitively appealing tool for studying transport. The massless direct electrons in graphene offer in the most distilled form the feature, the simple coupling between momentum and a spin-type degree of freedom, in this case the pseudospin, that we needed for unveiling a hitherto unknown inconsistency of various existing approaches. Although they agree in ordinary applications, they are in general not equivalent with some degree of freedom. Typically, a spin or band index is not treated semi-classically. Furthermore, we have shown how one solves analytically the resulting spin-coherent Boltzmann equations for Dirac electrons in randomized impurities. The thereby derived quantum corrections to the Drude conductivity offer one possible contribution to an observed and so far unexplained shift in the conductivity of graphene. We've also unveiled a special case where these rather difficult equations become relatively simple, namely in bilayer graphene with point-like impurities. There we can take the electron-hole coherent quantum corrections into account to all order, which results in a conductivity minimum. We have also worked on theoretical aspects of spin-coherent and Boltzmann equations related to semiconductor systems with a small Rajba spin-orbit coupling. On the application side, we have derived spin-coherent two-body collision integrals and addressed the problem of interplay between electron-electron interaction and different types of spin-orbit coupling. In particular, we can explain the infinite lifetime observed in experiments on the persistent spin helix. We also, within a band-coherent phenomenological Boltzmann approach, address the thermoelectric properties like the Nernst effect in strongly correlated systems to show that electronic correlations can lead to an increase of the Nernst effect beyond the semi-classical summary results. Okay, and there's the references, and that's from www.pks.mpg.de. So, January 1st, 2013, my thoughts. The math equations for the core of the UFO spaceship. The keywords found in the data from previous research continues in the next video. So we're still going over the keywords from that previous video that was back about 20 videos, okay? Thanks for watching.